Hi class, we're finally in chapter 7 in unit 3, which is where we begin stoichiometry. And stoichiometry will be with you for the rest of your chemistry career, whether it ends in grade 11, ends in grade 12, or you become a chemist. Everything is done in some stoichiometric way. And it's also just a fun word to say, stoichiometry. Really, it's all about the ratios amongst reactants and products. And ratios can be in terms of coefficients. And I'm going to show you that now coefficients can be turned into mole ratios. And mole ratios can be then turned into mass ratios as well. We can actually look at the mass of reactants needed, predict the mass of the products produced, all because of stoichiometry. Let's start off with a fun example. If we were to make s'mores for the class. So let's pretend we have 25 people in the class, and for each s'more we need 1 marshmallow plus 2 graham crackers plus 6 chocolate squares. I like mine to be very chocolatey. And that produces 1 s'more. If we want to produce, so we are changing the ratios based off of how much we want to produce of something. We want to produce 25 s'mores. You guys know intuitively what to do, which is great because hold on to those instincts, hold on to what you've learned in other classes. If we want to produce 25 s'mores, we have to multiply everything else by 25. So instead of 1 marshmallow, I need 25. Instead of 2 graham crackers, I now need 50. And instead of 6 chocolate squares, I now need 150 chocolate squares. And you combine those all in the ratio of 1 marshmallow to 2 graham crackers to 6 chocolate squares to get 1 s'more. If you combine 25 plus 50 plus 150, you get 25 s'mores. That is the same for chemical reactions. So here I'm showing the combustion of methane. 1 CH4 methane particles plus 2 oxygen molecules is going to react to form 1 carbon dioxide molecule plus 2 water molecules. So now our our ratio is 1 methane to 2 oxygen produces 1 carbon dioxide and 2 water. Now I can change this to moles. So 1 mole of methane is going to react with 2 moles of oxygen to form 1 mole, oops, I forgot to write mole, of carbon dioxide and 2 moles of water. Well, we spent all last unit, was it last unit or the unit before? I think it was, chapter. We looked in chapter 5 that moles can actually be represented in mass as well. So if I have 1 mole of CH4, that's going to be how much? 16 grams of CH4 is going to react with 64 grams of oxygen. I'm just going to put an equal sign, but it's, it's the colon as well. It's going to react to form how much? 12 plus 32, 44 grams of carbon dioxide and 36 grams of H2O. Well, let's have a look at this. If I did this correctly, 16 plus 64 is 80 grams of reactants produces how many? Well, hopefully, no surprise, 80 grams of products. So this is the power of stoichiometry, looking at the coefficients, changing the coefficients to mole ratios, and then changing the mole ratios to actual masses using molar masses off the periodic table. I can predict that if I combine 16 grams of methane with 64 grams of oxygen, I'm going to have 44 grams of carbon dioxide and 36 grams of water being produced. And because of the law of conservation of mass, it's exactly 80 grams of reactants reacts to produce 80 grams of products. Hopefully this makes sense to you. If not, rewatch this over again because it's really important to look at how, let's see, this is the coefficient ratio can be changed to the mole ratio that can be changed to the mass ratio as well. So let's have a look at an example. It says, so we have the production of water from hydrogen and oxygen. It says, write the ratio of hydrogen molecules to oxygen molecules to water molecules. Well, it's 2 hydrogen molecules react with 1 oxygen molecule to produce 2 water molecules. And I'm just looking directly at my coefficients here. That's why it's so important to know how to balance. And it says, how many molecules of oxygen are required to react with 100 molecules of hydrogen according to your ratio law from A? So we are scaling up here. If you need 100 molecules, or sorry, you have 100 hydrogen molecules, and if the original ratio is 2 to 1 for oxygen, how much did you increase 2 by to get to 100? Well, you multiplied it by 50. So you're going to multiply this by 50 as well, and you get 50 oxygen molecules. Okay, so therefore, 50 O2 molecules are required. Another way you can represent this is by fractions, which I know everybody hates, but I love. And I'm just doing the ratios. If there's 100, so actually, let me explain this. I wrote that too fast. So you're always comparing what you have. So these are going to be my hydrogen and oxygen numbers. So if I have 100 molecules of hydrogen and I want to find out number of oxygen molecules, it's going to be X, and my numbers are, it's 2 to 1. So then I can just rearrange this and get X equals 50. You get to the same point either way. That is more useful when you are dealing with strange numbers or uneven numbers like 2,478 molecules of oxygen. So it says how many molecules of water are formed when 2,478 molecules of oxygen are reacted with hydrogen. So we're assuming that there's lots and lots of hydrogen. So I'm going to set up my fraction equation, and I always put, so this is going to be H2O, this is going to be O2, my numbers on both sides. And I'm always going to make my X be on the numerator just because it's easier. So I'm trying to find out how many molecules of water are produced when you have 2,478 molecules of oxygen reacting. And the ratios are that for every 1 oxygen reacted, you have 2 molecules of water being produced. So when you rearrange this equation, you're going to get 2,478 times 2 over 1 equals 4,956 molecules of water produced. And you can just think about it intuitively. If one oxygen produces 2 waters, well, if you have 2,478 molecules of oxygen, double that, and that's how many molecules are produced. But you do have to be able to write out the mathematics of it to prove it. Okay, so how many molecules of H2 are required to react completely with 6.02 times 10 to the 23 molecules of oxygen? So again, we're going to look at, I need hydrogen, I have oxygen, my X goes here, and I have 6.02 times 10 to the 23 molecules of oxygen. My ratio is that for every 1 oxygen consumed, 2 hydrogen particles are consumed as well. So when I rearrange it, it's 2 times 6.02 times 10 to the 23 over 1, and I get 1.20 times 10 to the 24 molecules of H2 required. Okay. All right, let's look at another example. Vanadium can form several different compounds with oxygen, including V2O5, VO2, and V2O3. Determine the number of moles of oxygen that are needed to react with 0.5 moles of vanadium to form divanadium pentoxide. So it's V2O5. So first, this is 2 vanadium for every 5 oxygen. And so if it's asking to find how many moles of oxygen are required to react with 0.56 moles of vanadium, let's set up our equation. I'm putting number of oxygens over here. Oh, I put O2, it's just O. And then I'm putting, oh, see, I did it over here too. When oxygens are in a molecule, they're just by itself. It's only when oxygens are elemental that they form a diatomic molecule. And I'm sorry, my house is very loud right now. I hope you guys can't hear that. Okay, so we need to find the number of oxygen molecules needed, and when there's 0.56 moles of vanadium. Let's use our numbers from our ratio, 2 to 5. And now you can see why it's important to be able to create these ratio relationships, because this one I can't do in my head. I have to multiply 0.56 by 5 and then divide by 2. And I get 1.4 moles of oxygen is required. And the only way I can do that is by writing out the mole relationships. Okay, all right, so that's it for today. And try the other questions out. Let me know if you need any help with anything else, and we can work it out. All right, good luck.